All right, so today we want to look at some more exponential growth, obviously, and things like that. Let me give you just a silent moment to read this scenario. It's not on your sheet. Can you guys just read this about Jack? Ready, go. Read silently. Go. Okay. So, is it long enough for you? We got Jack. He's studying. He's a scientist. He's doing some research in the lab, and he's watching bacteria grow. The first thing to say is right here. He knows the colonies always grow exponentially. Let me say something quickly about why that's true, because it's not necessarily like that seems like a big assumption to even assume that a population would grow in this way. We've been studying these functions. It's a big leap to be like, okay, let's move to the real world. Why would we expect a population or anything to grow exponentially? And here's the defining feature of exponential growth. We say that something grows exponentially and has this behavior. This will happen. This kind of behavior will happen if the growth rate is proportional to the population size. That is, the bigger a population is, the faster it grows, for example. Now, think about this. It's going to feel like health class for a second, but think about like the world population, for example. It makes no sense for the population to always increase by 2 people every year. It makes no sense, right? Because as the population gets bigger, well, again, I don't want to sound too much like health class, but like our baby making capacity gets larger too, doesn't it? Like we have more people to make babies, right? So it makes sense that it wouldn't always be 2 babies per year. As the population grows, we would expect the growth rate to increase as well, not just, not only are we growing, but we're also growing faster, right, than we were before. So anytime that happens, that as a population increases, or as something increases in size, its ability to grow faster is proportional to its current size. That's the hallmark of exponential growth. Also, that happens with exponential decreasing. We call it exponential decay. For example, the amount of radioactive isotope in some thing, like radiometric dating, if you use carbon or whatever else, over time, the amount that remains is proportional, the growth rate, or in this case, the decay rate, is proportional to the amount that's there. It is able to decay, it decays more, at a rate proportional to the size or the amount of material that's there. So there are lots of things. Another thing that grows exponentially is your bank account, right? If you have an interest rate, let's say that you have an interest rate of 3%, even though that's a complete fiction. That is, every year you get 3% on your bank account. Well, what kind of bank accounts grow more quickly? Well, big ones, right? As your bank account grows in size, if you get 3% interest, that means more for a big bank account than a small bank account, right? If you have a huge bank account, it has more ability to produce interest. Its amount of interest it gets is exactly proportional to the size that it is. So that's another example of exponential growth. We have the opposite happening with your loan. If you take out a loan, now the balance on your account is growing exponentially. That's not good, right? Like they're charging interest against you, right, on a house or on whatever else you might take a loan out on. So we can see why exponential growth might be desirable sometimes or not desirable other times. So I hope that makes sense why for a population of bacteria that we expect some exponential behavior, right, in the growth pattern. We should also add a caveat there, right? It's not necessarily true that we get perfect exponential growth. For a while we might, and with perfectly unchecked populations, then we do expect exponential growth. But obviously there will be in the real world we'll have environmental constraints too. Food, resources, size of, land mass, whatever we have. presence of predators, etc., that would maybe mess with this model. But in a pure unchecked population growth environment, we get pure exponential growth. Yeah. So, all right, with that in mind, we have some questions. He says, how many points do I need to observe along the way? How many do I need a data table of like 10 observations? What do I need? Is it 3? How many can I get away with in order to figure out what this exponential growth model looks like? That's his question, right? And we need to maybe explain our reasoning around that too. Well, let's give this a try, and then we'll see if we can come up. There's already some foreshadowing here. If you look at the worksheet, you already know maybe what the answer is. How many pieces of data we need. So you have this now on your top of your sheet there, along with these pictures. So he has 2 different colonies he's been observing, and he's got this data here. This is a time axis, and this is the population of bacteria along the y-axis. Okay, so how many bacteria were there in this petri dish, colony A, to start with? 4, right? How many were in this one at the beginning? You can't tell, actually, right? We don't know. All right.
No, we started like 2 minutes.
Yeah, maybe we know at a certain time how much it was, but we don't know back at like.
Wait, are those 2 minutes or 2 seconds?
Did it say?
Yeah, it says hours.
I think it's hours,
Time in
right?
hours.
It's all actually.
Then
So
2 hours.
at the 2-hour mark, we happen to know the population, but we'd like to know what was it originally in the petri dish, right? We don't know. So what are the unknowns? Well, we've been talking about this formula in the red box over there. The unknowns for both of these, you don't need 2 boxes. They have 2 boxes on that sheet for this. You don't need both boxes. The unknowns are the same. What are the unknowns here? If we want this is like going back to algebra 1, for example. Did y equals mx plus b, and you had to figure out if you want to find the equation of the line, you needed to find like m and b, and then you were done, right? So here, what do we need to know to be done?
A, B.
Yeah, we need a and b, these constants. Keep in mind that a and b are constants, and y and x are variables, right? So we'd like to know the value of these 2 constants, right? And what is A again in terms of the actual context of the problem? What does A represent? Yeah, it's the y-intercept, but it's also, in our context, the... What'd you say? Yeah, it's the bacteria you start with. It's the initial population, whatever you want to call it, right? And B is, after having a lengthy discussion about B over here, what's B do for us?
It's how much it's increasing by each time.
Yeah, and we want to be specific. It's like a multiplier, right? It's like, we might call it the growth factor. It's something we multiply by each time. So that's what B does. All right, so yeah, in colony A, we actually know one of those things already, don't we? What is it? A is what? What's A? We already know A is 4, and we don't know what B is, right? But we do know that if we plug in 6, we get 2,916, right? That is, if we plug in 6, we get 2,916. Do you agree that that's something we know?
Yeah.
This might not be helpful. I'm just saying, isn't that what this says? If you plug in 6, you get 2,916. If you plug in 6, you get 2,916.
Why are you writing
2916 is the y coordinate you get when you plug in 6 for x. And in here, the a value is 4. Actually, so we already know that, right? Let's write down 2 similar. Can you write down 2 statements about colony B? That is, use this equation and plug in 2 and 12 and 8 and 768 to create for yourself 2 true statements involving A and B. Go ahead and do that if you haven't already. Colony B. Can you write down 2 statements of this form? Right here. Because we don't know A in this. In colony B, it's a little weirder, right? We don't know A. But can you write down 2 statements, 2 equations involving A and B that are true based on the 2 data points we have? Okay, give me one of them. Give me one of them, Sandra. What's one of the two equations you came up with? Like I said, an equation of this form right here, right? But for the second, for colony B in pink, well, give me an equation like that you wrote down for that one.
7, 6, 8 equals 8B.
Yeah, did you hear that back there? Say it one more time, Sandra.
7, 6, 8 equals 8B to 8.
Yeah, 7, 6, 8 equals AB to the 8th. All right, and then give me another one, Dylan. What's the other one?
12 equals AB squared.
You got it, right. So now we have two statements that we happen to be true about A and B. Okay. Can you figure out for colony A, can you figure out, please, we have A. Can you figure out what B is, please? Go ahead and do that on number 3 if you haven't done it already. We have an equation that only has one unknown, B. Can you figure out what B is? I think you can. Go ahead and do it. That is, solve this equation. Okay? Solve that equation.
I think it was, oh, yeah.
What's 2,916 divided by 4? All right, and then you may never had the occasion to take a sixth root before, but today you do. Okay, so I think I can probably guess the answer now. But what do you think the sixth root of 729 is? What'd you get? Did you all get 3?
Yeah.
Okay. I know, that's what I mean. You kind of can make a little bit of a guess here, especially since it ends in 9. It's clearly divisible by 3. All right. It's also divisible by 9. So that's not where we want to stop, though. It asks, let's make sure in math we always want to answer whatever was asked. So the actual question asks, what's the model? So we haven't answered that. The answer is not B is 3. The answer is, actually, please give the exponential equation. What is it? Y equals what? 4 times 3 to the x power. And on both of these problems, when we're done, any of these problems you do for homework tonight too, you can always check it, right? If you plug in 0 to your purported formula, do you get 4? If you plug in 6, do you get 2,916? Check it. If you know if those two things work, then I think you're right. By the way, this suggests an answer to the question I posed on the first slide, and that's how many points do you think we need in order to determine an exponential model? I think it looks like all we need is, well, we need 2, right? We're going to do it again here. All right, so I think I have your equations written down that you said to me, Sandra and Dylan. Here they are. Yes? For the colony B, we'd like to do the same thing and have in a box when we're done, y equals something times something to the x. That would be great. Sal, what do we have here? We have 2 equations, but we have 2 unknown variables, right? What are we looking at here? That's called anytime we have 2 equations or more. Yeah, it's called a system of equations. And you have solved some systems of equations before. In Algebra 1, you would have had experience solving a system of 2 equations, 2 linear equations in 2 unknown variables by using one of 3 different methods that you might remember. Okay, so bring that back to mind. We have 2 equations. Maybe that's enough to find the 2 unknowns that we have. Yeah.
Okay, I was able to figure it out, but like the way I did it, I made a lot of assumptions.
Okay.
So like, I used the equation 12 equals A equals 2.
Yeah.
And that would basically be 12 equals A times B equals 8.
Okay.
So I tried to find a square that was small enough to fit in.
Okay.
And I got.
I love, and it worked. Did you get it?
Yeah,
Yeah, in the end, you got it, right?
I got 3 times.
Yeah, on both of these, you probably could just like stare at them long enough and like just kind of nut your way to the answer. Just kind of like just trying some numbers and being like, okay, well, if I multiply, by this, it seems to work. I've got lots of 2s. It seems like, so I think you're right. But I think that strategy will fail you on the next example I give you. So let's build up a slightly more robust technique. There are a couple different strategies that you have maybe you've used before in your life that would maybe work. Like for instance, I like substitution. If you've solved a system using substitution before, that works here too, and it works great. So that's an option for you if you don't like the way I'm about to do it. But here's a slick way that I'm going to show you to do it. I don't know that you would think of it necessarily yourself, so I'll just show you. I'm going to divide the first equation by the second equation. Now notice how I wrote these. I wrote these in this order so that I could do this nicely. Now you might be thinking, why would I do this? Well, you'll see right away when we look at the other side. What is ab to the 8 divided by ab squared? Careful, what is it? I like some of what I heard. It's what? ab to the 4. What is it, Jessica? It's just b to the 6th, isn't it? In fact, this is the reason I did this. You agree? That the a's go away? That's why I did it, is so that I could get just b to the 6th here. Do you see why that's desirable? You might be like, wait, why, 8 went away, that's not good. No, actually, that's exactly what we wanted to happen. And over here, 768 divided by 12 is something. 64. And in just 1 second from now, we're going to know what b is and be halfway done. More than halfway done. What's b? You could probably guess even without taking the 6th root on the calculator. I promise, by the way, you'll be taking roots besides 6th roots somewhere along the lines here too. Just so happens to be that that's what we have so far. So we're good. We got b, didn't we? Wonderful. How do we get a? Talk to me. Say it one more time. Sorry. Where? Yeah, plug in b. I like that idea. Where? What are you talking about? Yeah, in either, this is the key here, right? If you'd like to know what a is, go back and plug 2 in for b in either one of these two equations. If you're a lazy mathematician like me, you might pick the second one, right? Just because it's easier to plug in 2 to this equation. So if you plug in 2 for b, do you think you can figure out what a is? I think you can. Yeah, it's definitely 3, even just by observation you could do that. And then again, don't forget to actually write your answer out. It's 3 times 2 to the x. Yeah, another way to find it would be just to think, okay, once you know that b is 2, well, what would a have had to be? What would the initial population be if after 2 hours it's 12? Well, what was it after 1 hour? 6, and at 0 hours it was 3, right? You can just divide by 2 back a couple times too. Anyway, I just want to make sure you see the big picture here too. Wonderful. I have 2 more examples that are a little trickier. Are you ready for? You think you're good at this?
No.
I'm gonna throw these at you. Here we go. These are not on your sheet. Let's try these. Here. Just for fun. Yes. Already there's something awry here, right? We got something a little different than before. Both of these are a little weird, right? Write these 2 problems that I have up on the board on the back too, or you can do them anywhere you like. I just would like you to do these problems too, like the 2 we have on the board as well. Along with those 2 problems. Yeah, those 2 problems. Sure. Well, this is just everything we do is simple.
So if it's just for fun, that means it's not required.
Well, no, your grade is up.
Now you're just messing with
You had some help getting started, at least? Oh, yes, ma'am. All right, give those a try. The ones on the worksheet are a little easier. I really want you to try these 2 though, because I feel like you need an extra challenge in your life. Okay. Take a picture. Yes, the sheet that I just gave you. Along with these 2 problems. You haven't heard about it yet. The instructions are the same on all of it.
It's hard to believe you're like that.
See you tomorrow.
There will be
It was.
See you guys.
I can't hear you.